Hello everybody, welcome to the conservation theorems in electrodynamics part 2. Part 1 was on the conservation of energy in electrodynamics. There we had seen that electromagnetic fields possess energy. Part 2 is on the conservation of momentum of electromagnetic fields. We begin with an exercise where we will see why electromagnetic momentum is a must for the conservation theorem. We know when on move, a charge creates a magnetic field surrounding itself. The direction of which is given by the right hand rule. This magnetic field applies a force on a nearby moving charge. Now consider charge Q1 is moving towards the origin along x-axis, and charge Q2 is also moving towards the origin but along y-axis. V1 is the velocity of charge Q1 and V2 is the velocity of charge Q2. Now let us look at the forces acting on these charges. First, electrostatic force. Force on Q1 by Q2 act along T1 Q2, so this is the direction of the force. Similarly, force on Q2 by Q1 acts along Q1 Q2, and this is the direction of the force, so we write down F1 on Q1 by Q2. Similarly here this is F21. The forces are equal and opposite, and this is in accordance with the Newton's third law. Next we see the magnetic fields of the charges in motion and the corresponding magnetic forces. Q1 is moving towards the origin, so magnetic field will be circled in a direction which is going into the page. Now if this represents the direction which is coming out of the page, then the magnetic field at the point of charge Q2 due to charge Q1 would be in a direction which is going into the page, so this would be along this direction. Charge Q2 is moving towards the origin, and the magnetic field at the point Q1 due to its motion would be circled in a direction which is coming out of the page. This is the direction of the velocity, and this is the direction of the magnetic field caused by the charge motion of the charge Q2. So according to Fleming's left hand rule, the direction of the force will be along positive y-axis, and at point Q2 this is the direction of the velocity, and this is the direction of the magnetic field which is caused by the charge Q1. So the direction of the magnetic force will be along this direction. That is, charge Q1 will force charge Q2 to move along x direction, and charge Q2 will force charge Q1 to move along y direction. Since the ratio of the magnetic fields, that is B1 by B2, is equal to Q1 V1 divided by Q2 into V2, hence the ratio of the magnitude of the magnetic forces, that is Fm1 to Fm2, Fm1 represents the force on charge Q1 by charge Q2, and Fm2 represents force on charge Q2 by charge Q1, equals to 1. That is, the magnitude of the force on charge Q1 is equal to magnitude of the force on charge Q2, which we can write is equal to Fm. However, even though their magnitudes are equal, but they do not cancel each other. Their directions are different. Now this apparently violates Newton's third law. The violation of Newton's third law would also imply the violation of the conservation of momentum. This is because we know that the momentum of a body is related to the applied force on the body via Newton's second law. Now the question is how to solve this crisis. Fortunately, the electromagnetic field itself has the solution, because electromagnetic field has got its own momentum, just like the fact that electromagnetic field has got its own energy. In the next section, we will see when the electromagnetic field momentum is associated with the mechanical momentum, then the conservation law is satisfied. According to Newton's second law, the force on a body is equal to the rate of change of momentum of the body. So we can write F is equal to Tp suffix mechanical to represent its mechanical force dt. we consider a uniform collection of charges distributed over a volume V. Then the Lorentz force acting on the charges is given by where rho is the charge density, or we can write down in place of rho multiplied by V, we can write down the current density term, which is cross product with the magnetic field. Replacing rho and J using Maxwell's equation 1 and 4 respectively, and using the product rules given by A and V, we can arrive at the final expression F is equal to integral over volume V bracket epsilon naught, again bracket, divergence of E into E plus E dot divergence into E, 1 bracket closed, plus 1 by mu naught bracket divergence of B into B plus B dot divergence into B, 1 bracket closed, minus half into gradient of bracket epsilon naught into E square plus 1 by mu naught into B square bracket closed, minus epsilon naught del del T bracket E cross B bracket closed, again bracket closed, d tau. The reason of writing F in this particular form is that F can be expressed in terms of Maxwell's stress tensor, which is given by thus, the first three terms of F can be expressed as divergence of the Maxwell stress tensor. Writing force in terms of Maxwell stress tensor, we can write F is equal to volume integral V, divergence of Maxwell stress tensor T dV, minus epsilon naught mu naught d dt of volume integral V S into dV, where S is the pointing factor. Thus, in this expression, T has the dimension of force per unit area. Precisely, Tij represents the force per unit area along the ith direction on a surface which is oriented along the jth direction. So, in that respect, Tii, that is all the diagonal terms, represents the stress force per unit area, and the off diagonal terms represents shear. S in the last term represents the pointing factor. Now, replacing F in Newton's law, we get thus, we arrive at the momentum conservation law. Finally, we write down here T with a negative sign is the momentum flux density. P mechanical and P electromagnetic together represents the momentum charge density. Thus, we see momentum of an electromagnetic field must be added to the mechanical momentum for the momentum conservation law to hold. Thank you very much for listening. Hope you would find this video useful for you. Please share if you like it.